Okay, we will introduce fluid pressure, which then leads us to fluid force, and we're going to be calculating the force that a fluid puts on a surface, and it's all pretty much based on this fluid pressure. We define pressure, the fluid pressure, as, well, W times H, where W is the weight density. We saw this before with water in our work problems. W is the weight density of the liquid. And that would be per unit volume. And like we said with the work problems, water was 62.4 pounds per cubic foot. So that may play a part in these as well. And then the H in our formula is the depth of the object.
Height?
The height, in these types of problems, it's better to think of it as depth, but we can again think how far down in the water, what's the height of the water. So yeah, that would work. Okay, so that's the fluid pressure. That's the pressure on one particular object. But as we extend this, we want to know the total force being applied to a surface. So the fluid force, that is simply the pressure times the area of that surface we're looking to find the total force on. So like the side of an aquarium, okay, it's going to be the pressure times the area of that side. If it's a rectangular side, the area would be base times height, length times width. So we'll be dealing with area times this pressure up here. Or we can just go ahead and make this one formula, W times H times A. And let's go ahead and take a look at our worksheet 7.7. And first of all, we'll take one of the ones that you want a lot of, I'm sure. Let's look at number 4. This one's very straightforward. But it kind of gives you an idea what we'll be dealing with. And the problem on 1 through 4, it says the area of the top side of a piece of sheet metal is given. The sheet metal is submerged horizontally in 8 feet of water. Find the fluid force on the top side. So we have this sheet of metal, horizontal, and we have water. You like my water? 8 feet of water on top of this horizontal piece of sheet metal. Well, we're given in number 4 that the sheet metal is 25 square feet. So that'll be, we don't know if it's a rectangle or a square or anything like that. We're just given the actual area. We don't have to do any calculations, thank goodness, for the area part. So the fluid force, the total fluid force here, every point on this piece of sheet metal has exactly the same depth of water having force on it. So simply the pressure times the area, or the weight density times the depth times the area. The total force on the sheet metal would be, well, the weight density for the water is 62.4 pounds per cubic foot. I guess I should show my units here. And then the depth, every point being 8 feet, gives us that, and then times the area. Now, what units would we be left with when we multiply these numbers?
The pounds?
Okay, we've got cubic feet in the bottom, we've got feet times feet squared in the top, so feet cubed divided by feet cubed, we're left with just the pounds. And 62.4 times 8 times 25 would give us our total force on this horizontal plate.
Yeah, I'll do the calculation.
Okay, I'll let you do the calculation. So for this plate, we get the 12,480 pounds of force. Now that's over the entire plate, that's not just at one particular point. But you can see the pressure of the water, you go down far enough, this is why they haven't been able to go down to the Titanic and swim around and fish things up. There's just so much, it's so far down in the ocean, there's so much fluid pressure on it that they have gotten specialized robots, for lack of a better word, but the highly pressurized to where they can withstand all that pressure. They'll go down and check out these buried treasures.
I think during the 1960s or just during the 90s, I don't know, but it was like 60s or 90s. They built like this huge submarine, and they went to the Mariana Trench.
Yeah. So that's why submarines, that's a good example. They can only go a certain depth before there's too much fluid force and it'll crush the submarine. So that's part of the idea of designing these things. Now, the problem we're going to look at is not just a horizontal, what's the total force on a horizontal plate, but what's the total force on a vertical plate. And we're going to look at that in a little bit different way. Same idea, but the main difference will be the fluid pressure here is different from the fluid pressure up here. And the fluid pressure down here would be greater than the fluid pressure at the top. So we've got to take that into account, but it'll be using these same equations, except it'll be integrating, okay? And let's take a look at what we can do there. Okay, we're going to take an equilateral triangle and submerge it to where, let's see if I can draw an equilateral triangle, not too bad. Submerge it to where it is 1 meter below the surface of the water. And in metric terms, the weight density 9,800 newtons per cubic meter, whereas in the English version it's 62.4 pounds per cubic feet. So there's W. Of course, W is going to be the easy one to find. It'll be, just make sure it's the right constant. But we've got fluid force is weight density times depth times area. Now, the problem here is, since it's a vertical plate, easy for me to say, huh? The depth is going to be different at each point, except for each little horizontal slice. Now, we're going to make this slice so thin that it's basically approaching zero. So we can say the depth at each one of these points in this slice will be the same. So that's what we're going to have to calculate and work with. Think of this slice. Now, I guess we didn't say what size of equilateral triangle. We'll say it's 3 meters on each side. Okay. That will make a difference on the slice. Now, the depth of our slice, well, what shall we call that? A lot of that is going to depend on where we put our axes. Where's our coordinate axes? X-axis, Y-axis.
Well, how do you get that 3?
It would be given to you.
Oh.
That's one of the details that I forgot to mention
That's one
up
of the
here.
sides, right?
3 meter sides on this equilateral triangle.
Okay.
Okay? My goodness, my handwriting isn't very good, but anyway.
That's fine.
Okay. Well, where do you want to put the coordinate system? We have a choice. We can put our x-axis down here. We could put our x-axis, well, we could put it right here, or we could put the x-axis clear on top, on the surface of the water. Okay. Put it on the bottom. We could do that. Now, there's benefits to all 3 of these places, but there's also
Shortcuts?
problems in all 3 of these places. So one place might be better for one reason, but turns out to be worse for another reason. It's really not going to matter all that much as long as you say, this is my x-axis. Now, the y-axis, we could put the y-axis anywhere as well, but probably the y-axis is going to be best right through the center. Okay. And in most of these, well, for rectangles or squares, the y-axis might be best on one edge of it. But for the others, equilateral triangle like this, probably through the center. Now, if it was a triangle where one side was vertical, okay, then maybe the y-axis on that would be best. But this case, definitely the y-axis through the center will be the best choice. And like I said, the x-axis, that really doesn't matter. So let's go ahead and put it down here. Okay. So this point right here will be 0, 0. That'll be our origin. So our depth, h, down to our slice, h will equal what?
The changing. I mean, because you could take a slice from, right? You can take a slice from everywhere, right? Anywhere in there.
Yeah.
So it'll be, would it be 1 minus y?
Well,
'Cause
this
one-
is the tricky part. When we put the y-axis down here, that's where we.
It's a DH plus 1, right?
Well, the DH, we have to think of that not DH or delta H, okay? The thickness, the width of this little slice will be our delta, but that's not talking about the depth.
Wouldn't it be like dy?
Yeah, we'll call the thickness delta y. So there's going to be the differential, where the differential comes from. But the height, let's
Since
see.
it's one, I mean, since it's one. Oh, but that's, okay. Since our x is in the bottom, then it'll be,
This makes it very interesting to put the x-axis down here. It can be done, and like I said, this is the one place where it gets rather difficult putting the y-axis down here.
so if you.
But there's other things that will kind of make up for it. We need to find out how high the water is. We're saying this would be y equals 0. How high is the water?
4?
No, not 4.
I mean, it's 1 plus the.
Yeah, this would be 1,
plus
but
the triangle.
what's the, I guess we're using height, we're using h too many different places, but what's the height of this triangle? That's one thing we need to figure out. We'll
I mean,
use.
We can use the area, right? The area of an equilateral, which is not base times height, huh? Divided by 1/2.
Well, that's the area of any triangle,
Yeah,
but we
equilateral?
don't know the area, so that's not going to help us.
But we know the sides.
We do know the sides.
I mean, it'll be 1.5.
Side of 3, side of 1.5.
Is that why we made it? Because that's going to make it 2 right triangles, right?
Correct. That is the huge benefit of putting the y-axis down the center. Okay. So yeah, from here then,
Oh, you
Pythagorean
can use
theorem.
Pythagorean theorem, yeah. So it'll be 3. So it'll be 9 minus 1.5 squared.
And we'll get fancy here with 9 minus 9/4 or 36 over 4.
So it'll be 36. So it'll be 25 over 4.
So yeah.
So it'll be 25.
20,
5 over 2.
not 25. 36 minus 9.
27. So it'll be 27 divided by 2.
Which you could actually 3 square root of 3 divided by 2.
9 times 3.
So 3 square root of 3 divided by 2 is our height of the triangle. So the total depth, the depth down to the bottom of the triangle, is going to be 1 plus that. Like I said, we're using h too many different ways. This h we're representing as the depth of our slice. But we need the total depth to be able to figure out the depth of the slice. Now, ultimately, we're going to call, since we've set the y-axis here, from here up to the slice is going to be our y value. So the depth will be what? Depth will be represented by what? What's our total depth?
1 plus 3. Yeah, 1 or 2.
Okay, that value minus the y. Correct. So that total distance minus the distance where the slice is. And that gives us our depth, h, of that slice. Okay. Okay, so we've got W, we've got H now.
Which one is the W? Oh, the W's will be that because it's getting
Yep.
there.
In the metric, it'll be 9,800 newtons per cubic meter. Now, it's going to be a different value if it's in some other, like, I guess, erg. Is erg the other force? That's dealing with centimeters, I think. Dyne and centimeters, and, well, I don't know. Don't remember all those, but those are some of the terms. Okay. Okay, so we've got one of the hard things figured out. The other hard thing is going to be our area. Area of that slice, well, it's going to be length times width, and we've already decided our width is going to be the delta y. What is that length going to be? And we are not going to have enough space on this little page. We'll move to the next one, but think about the length of each of these slices. Okay.
I mean, it will always be 3, right?
No.
Oh, no, because...
This one down here would be 3, but as we move up, it's getting shorter.
So it'll be a change in x?
You could think of that, yeah. Change in x, and it's going to be essentially this x value minus this x value, which doesn't make sense when you're talking length, but this x value is going to be a negative. So this x minus a negative will be adding, technically. So we've got to figure out how to represent this x and this x. I don't know if I can draw any more on that, make it any clearer or not, but well, we'll move to the next page. Okay, so we're down to finding the length of our slice, and as we said, it's going to be represented by this x value minus this x value, or a positive minus a negative, which will make it a bigger length. We just have to figure out how we represent that. Well, what do we know about these x values? As we consider different slices, how do the x values change? What are they based on? It's going to be on this line and on this line. Okay, so we need the equations of those lines. Well, that is the point 0 and what? And yeah, the height of that equilateral triangle that we calculated earlier. So 3 square root of 3 over 2 is the y value. Let's see, both of these that will be our y-intercept. So both equations we can set up this way. So we'll have y equals, well, we'll call this y2 since we're calling that x2. y2, the slope of it would be what? What's this point?
Y2?
Now the actual coordinates of this point.
1.5 and 0.
The x-intercept here would be 1.5. Remember, the whole side is 3, but from 0 being in halfway through the triangle,
So the other one will be negative 1.5.
yeah, and this will be negative 1.50. Okay, so that will actually help us find the slope, and we may want to go ahead and write that as 3/2 instead of 1.5. So slope of our second, or our line over here, change in y over the change in x, actually it'd be down, so negative. So change in y, we go down 3 square root of 3 over 2. We go over 3/2. So invert and multiply, and it actually turns out to be quite nice. Negative square root of 3 is the slope of that one. Not your nicest line for an equation, but it's not too bad. It could be worse.
It could be worse. I mean, if it goes worse, you can throw some things on
And then y sub 1, well, this time our slope, change in y is 3 square root of 3 over 2 up, and then over from negative 1.5 to 0, so over 3/2. So the slope of that first line will be positive square root of 3. We have symmetry as well, so it hopefully isn't too much to see. Slope, and once again, same y-intercept. Okay, so there's the equations of our two lines. But we don't need the length in terms of x. We need to see what x equals in terms of y. So solve each one of these. Okay. Whoops. Not squared, but x sub 2. And divide by negative square root of 3. Or, even though it looks uglier, thinking multiply by the fraction. I think it's going to be nicer as we simplify the form. Multiply that through and we'll have negative times a negative, square root of 3's cancel out. Okay, so there's our x sub 2. That's going to be the right side of our every slice. And the left side, solve for x sub 1.
I was going to ask, can we just make the other equation the opposite?
Yeah, that's what
It basically turns into the opposite. We can verify it right here. Yeah. So we can see both of these. I mean, multiply one by a negative and you got the other one. And so technically it's almost like saying, we could just say 2 times x sub 2. Basically going from 0 to x sub 2, and
So
then
is this symmetric?
because they're symmetric, we can say 2 times that. So, okay, all of that to determine the length, 2 times, and, well, let's use that one. So our length will be that. Okay, now, have we forgotten what we're actually doing here? Fluid force, WHA, okay, the W was the 9800, the H was our 1 plus 3 square root of 3 over 2 minus Y, and then A would be length times our delta Y. So now we're ready to set up our integral. We'll be integrating from where to where? Such lovely values here. From 0 up to, right, 3 square root of 3 over 2. So, integral from 0 to 3 square root of 3 over 2. Now, this is where we see one advantage of putting the x-axis down at the bottom. We're going from 0, from y equals 0, up to the top of the triangle.
So the height will be the length?
Okay. Then W is our 9800. The H, the depth that we calculated, we said the 1 plus 3 square root of 3 over 2 minus Y. Okay. And then area, length times width. That length was what? Plus.
2 times.
Was that right?
Yep.
And then our times our width of delta Y
I think it was
turns
just
into the
3.
dy.
That was
Oh,
number 2.
that's right. It was just 3, wasn't it?
Yeah.
Okay, this thing isn't going to let me erase, so we'll just mark that out. The length we found was just plus the 3, right?
Yeah.
Okay. So, well, it looks ugly, but really it's, we're going to need to multiply the 2 binomials. That's probably the easiest way to do it. Multiply the 2 binomials. Well, it's not really a binomial. This will be a trinomial, but multiply that out. I mean, from here, it's just little algebra, and you'll end up with
You don't have to multiply.
power rule. Yeah, I think you guys can multiply that out.
As soon
So,
as we figure out how to
but
set
that
it.
would be the total fluid force on this equilateral triangle 1 meter below the surface of the water.
Can you go
Equilateral
over-
triangle 3 meter by 3 meter by 3 meter.
Oh, man.
Okay?
Can you go all over again, please? Force is equal to the weight.
Okay, so fluid force is weight density
Weight density.
times the depth times the area of our object.
Okay, so weight is gonna be constant because it's always gonna be.
Right.
That-
W will be
Always-
dependent on what we're submerging it into and what units. Probably
Is it-
always going to be water and either the 62.4 in the pounds per cubic feet or the 9800 newtons per cubic meter.
So if it's in meters, then it's 9800. So then the height will be 1 plus.
Well,
and-
the depth depends on where we put our x-axis. Okay, that might change. Had we put our x-axis up here, we'd have a slightly different representation.
Well, I'm always gonna
But-
do it on the bottom because you did it.
Okay,
So it'll be at the bottom.
but
So it'll be-
the depth is always from the surface of the water down to where our slice is. And in this case, we're saying this is our y value, so the depth is all of this minus our y value.
minus the y.
Yeah. So that's how we get our depth.
And then area.
And then the area, our slice is going to be a rectangle, so length times width, and of course the width will be our delta. The tricky part will be the length. And the length, well, in this case, is determined by two lines. We have to find the equation of the lines. Sometimes, if it's just a triangle like this, then the line, this line, vertical, so we don't have to worry about it. But we'd still have to figure out this line. It'd be the x value, find the equation of this line, and then solve it for x to put the length in terms of y.
So it'll be y equal mx plus b.
So yeah, if you have our y-intercept, you can set it up that way, and then you'd have to solve for x to get it in terms of y.
Okay.
Okay, and then you're ready to integrate. Well, your integral limits will be from the bottom of your figure to the top of your figure.
Okay.
And this one is probably as hard or harder than all the others that you'll see. You may see one as hard as this one, but most of them are a little less difficult. This one became a little more difficult because of the triangle, equilateral triangle. Just numbers were kind of tough to work with. Okay? Questions? All right, and that's 7.7. That'll be your fluid force. So good luck on that, and we'll work on these. We'll review for the test tomorrow, and test will be Friday.
This will be on the test as well?
Yes, this will be on the test as well.